Hi everyone, I'm Andrew and welcome to my YouTube channel. In this channel, I will show you some recent progress in organic synthesis. Because I'm a PhD student majored in organic synthesis, and all these topics are focused on organic synthesis. The detailed topics are like total synthesis of natural products, novel methodologies, chemical biology, self-assembly, drug discovery, synthetic biology, and some other topics. And if you are interested in these topics, you can follow me on the YouTube. Very fortunately, I had the opportunity to do some chemistry based on ditoponoid alkaloids. And recently, 3 papers are published based on the synthesis of arcutinine, the same molecules. And 2 groups are from China, and another group is from UC Berkeley. That is why I will focus the first topic on this molecule, arcutinins. And in this progress report, we will only focus on Yong Qin's strategy towards the total synthesis of arcutinine. Arcutinine is a type of C20 ditoponoid alkaloids, and it has very caged structures. But this structure is not so classic alkaloids. It is rearranged derivatives based on heptidine type alkaloids. Actually, in 2016, the same group have already synthesized the aldehyde archipropylene, a precursor for the arcutinine alkaloids, but there is no reported synthesis towards the final alkaloids. Let's have a look at Yong Qin's strategy towards the total synthesis of archipropylene, the precursor for the arcutinins. They start from the advanced intermediate 6. This structure is synthesized by intermolecular dearomatization diacetyl reaction. Then the appendage modifications to generate the intermediate 7. The intermolecular aldol reaction and the samyl-iodine-mediated reductive coupling to generate the intermediate 8. This compound is very close to the final product. Then they incorporate the quaternary structures on carbon 4 to generate the molecule 9. But the problem is the yield is not so high for this reaction step. Another one is the diastereomer selectivity is not so high. And when they tried a lot of different conditions to incorporate the nitrogen onto these structures, all these attempts are not so successful. That's why they want to publish another strategies towards the final product, arcutinins. Now let's have a close look at the retrosynthetic analysis of arcutinine. Inspired by their nature communication work, they first disconnect the carbon 10 and carbon 9 to give the intermediate 10. And this intermediate could be further simplified through the oxidative dearomatization and intermolecular diacetyl reaction to give the bicycle 11. And the very crucial pyridine scaffold is synthesized by the Arza-Wacker reaction. Then, the very complex caged structure arcutinine could be simplified to the cyclohexane scaffold 12. And among this scaffold, there is 2 quaternary centers. One of them is synthesized by the decarboxylative allylation. Another one is introduced through the conjugative addition based on the enone 15. The Nowenger condensation between the 1,3-diketone and the aldehyde could give the enone structures, followed by the reductive conditions and methylated of the enone could give the final product 19. Then methyl lithium was added to the structure 19 to attack the ketone, followed by the acidic workup of the reaction to give the 15. This structure undergoes the conjugative addition followed by the TMS trap of the enol could give the final product 20. Methylated lithium was added to the reaction to free the OTMS to give the lithium enolate. Incorporate with the HMPA, allyl chloride was added to the reaction to give the oxygen acylated product 21. Under the condition of the decarboxylative alylation, 13 was synthesized in 55% yield. Under the conditions of palladium chloride, the terminal olefin was isomerized to give the internal olefin, followed by the deprotect of the mom protection group, and then reprotect it again. Under the lithium aluminum hydride conditions, the nitride group was reduced to give the amine, followed by the protection of the TOS group to give the intermediate 23. Under the reductive conditions, the ketone was also reduced to the alcohol. Then 23 undergoes very crucial Arza-Wacker conditions to give the pyridine scaffold. But the diastereoselectivity is not so good, and the two diastereoisomers could not be separated on column, so they just used the mixture to do the reaction together, oxidation, deprotection, and followed by the dearomatization and diazide reaction to give the final cyclidation condition, cyclidation product 25 and 10. 10 is what they needed, and we can see that the structure is totally controlled by the stereocenters at carbon 20. So if they want to improve the efficiency of this reaction, they have to control the diastereoselectivity about the Arza-Wacker reaction. Based on the Arza-Wacker reaction, we can see the protection group at the carbon 10 could play a very crucial role in the diastereoselectivity control. So they tried different protection group like TMS and TBS. Actually, they expected when they use the TMS, the DR is 2.5 to 1, and when they increase it to the TBS protection group, the DR is 3 to 1. And then followed almost the same procedures, deprotect, oxidation, deprotect again, and oxidative dearomatization followed by the intermolecular diazide reaction conditions to give the final product in 59% yield from 28A structures. With enough amount of the compound 10 in hand, they started to investigate the reductive coupling between the ketone and alkene. Under the Samuel iodide conditions, only 10 minutes, the reductive elimination took place very smoothly. But when they prolonged the time to 12 hours, almost the same conditions, but the equivalent of the Samuel iodide should be increased, and the reductive coupling and reductive elimination could take place at the same time to give the final product 32 in 85% yield, and this step is very efficient to reduce the oxidative states based on the scaffold 10. Then they come to the end of the total synthesis of arcutinine. Under the Ishamasa's conditions, they install the exo double bond to give the product 33, and then reduce the enol ketone to give the alcohol in 77% yield. Then they add the appendage to the allylic alcohol, and followed by the deprotect of the TOS group to give the product 35 in 6 product yield. So there is only one step left for the completion of the total synthesis. When they use the PHIO conditions at 0 degrees, only a small portion of the arcutinine was obtained. When we look at the two scaffold, the imine in arcutinine is tri-substituted, which is much more stable than the structure 36. So we can imagine if we increase the reaction conditions, more arcutinine could be obtained. That's why they found that when the toluene was used as the solvent and 110 degrees, the reaction could proceed in 71% yield to give the arcutinine. Now they finished the total synthesis and the first total synthesis of arcutinine.